let's I will share my screen now. Okay. So first of all, let's talk about what thermal chemistry actually is. So we are talking about the transfer of energy. We are looking at how energy changes and at the exchanges between a certain system and surrounding. Okay, so first of all, first thing I need to be able to understand is the way we define a system or a surrounding. So that is really relative on scale, right? Because we can zoom into a certain reaction. If we consider a reaction inside of water, we can consider water as a surrounding. But if we consider the whole test tube or maybe like a beaker as a surrounding, maybe a sealed beaker, that could be a system in itself, and then the surrounding could be the environment around it, or we can consider the whole room that this a beaker is in as a whole system in itself, maybe some kind of sealed room. Then in that case, this is the system. The surrounding will be the outside environment, or you can think of Earth as a whole as a system. Okay, so you understand what I'm saying in terms of scale. We have three different kinds of systems. We have what's called a open system. We have closed system, and then we have isolated system. You heard of the difference between the three? Yeah. So open system is something that matter can flow through. So matter can flow through. But closed system, matter cannot go through. Isolated system, matter cannot get through right now. And matter, I'm considering gas as well, right? So that's things like when you boil off water, it can't escape through the cracks. Okay, something like a styrofoam cup. If you saran wrap it really tightly, then that could be matter. Can flow in and out. But energy, though, energy is something that um, can also be flown in and out in an open system. So open system, as I said, you have a cup with an open top. Closed system, cup is closed. Matter cannot go in and out, but energy can go in and out. So that's like heat, for example. It's one of the main energies that we think about. So you can lose heat. For example, if you leave like a styrofoam cup that's sealed tightly, you're still gonna have it, go from hot to cold maybe. So that will be indicating that the heat has been lost. Some energy has been transferred out of the system, from the system to the surrounding. But isolated system, I should write matter flow, energy flow. Energy cannot go in and out, and matter cannot go in and out. Okay? So a lot of the times when we're studying certain situations, certain systems, it depends. We have to consider: are we looking at a closed system right here? Are we looking at an isolated system? Or are we looking at an open system? Okay, so that's just a fancy term for if matter or energy is allowed to flow or not. Oh, whoops. Okay, so now I can go with this. Whoa, what is this? Okay, so one of the energy transfer we've studied before was the how carbon dioxide is cycled through along with energy. So carbon dioxide itself, that would be like a matter transfer. So carbon, sorry, not carbon dioxide, carbon cycle. So carbon transfer, and so that would be a matter. But energy wise, it's not really matter. It's not something that we can feel and touch, but it's definitely something that we can see that can do work. Okay, in physics, you've probably seen energy, you can convert that into work, right? Useful work. That's probably one of the the definition of energy. So here we see sunlight provides energy, right? We convert that, or we don't convert it. Plants convert that using photosynthesis, water plus carbon dioxide, giving you glucose and oxygen. And then what? In return, we eat it, right? And we use cellular respiration, as you learn in biology, right? The big picture is we're taking, in reverse, oxygen and glucose, returning it back to carbon dioxide and water. Okay, so there's different kinds of energy transformation. You see, so it's transformation. Sunlight energy, heat energy, has turned into chemical potential energies that's stored in glucose in this case. Okay, so that's an energy transformation. All right, another thing we need to know is the difference between heat and temperature. Okay, so there is quite a bit of difference. Usually we think of the more heat there is, the more temperature there is. Yes, they are definitely correlated, but they're not the same thing. Heat, we are talking in terms of energy. Okay, we're actually talking about the transfer of energy specifically. When we feel heat, we are feeling the transfer of energy from the air to our skin, right? So that's when we feel like, oh, there's a heat wave outside. It's really hot outside. Okay, so speaking of hot, but hot also refers to temperature, right? Temperature has to do with the average kinetic energy of a certain system. So if I'm saying this iPad is getting really hot, then what I'm saying is the molecules of this iPad are vibrating, translating, rotating at a very high speed. Of course, solid, we just think of it vibrating mostly. Okay, if it's a liquid, we can it definitely has more degree of freedom to move, right? It can vibrate, it can rotate, it can translate, and of course, gas molecules. There's even more degrees of freedom there. All right, so that's why when you heat up something, it will change state, right? It will increase in thermal energy or increase its in kinetic energy. Most of the stuff really comes from kinetic energy. Anyways, when we feel hot outside, it just means that the air molecules are going a lot faster. That's basically what it means. Okay, so does that clear up the difference between heat and temperature a little more? Yeah, heat is more about the transfer of that energy, and temperature, it's more about the inherent average kinetic energy of that system. Well, at that certain time. Okay, so for example, when a system loses some heat to its surrounding, then its average kinetic energy will go down, usually. And that means that the temperature will go down. Okay? So just relate temperature with average kinetic energy. Okay? If you ever studied kinetic molecular theory, which you probably have in earlier grades, you probably will remember that as well. Temperature is the average kinetic energy of a system. All right. So temperature, so let's see. A heat is the amount of energy transferred between substance. The unit would be joules or kilojoules. Temperature is the measure of the average kinetic energy of a particle in a sample of matter. Yep, so we said that. And then the units would be degrees, Kelvin, or Fahrenheit. Okay, so one is measured in terms of energy, one is measured in terms of Celsius. Or Kelvin, usually. We don't really use Fahrenheit here. So what are the products when a methane combusts in air? Okay, you know that. We don't need to go through that, right? CH4 is going to react with what for combustion? Yeah, okay, yeah. No need to go through that. Yeah, you know your combustion reactions. So energy that is released from this chemical system to the surrounding is called thermal energy. We can think of combustion reaction as something that releases heat, right? That's why we combust oil in our car. So we can turn that kinetic energy, turn that chemical potential energy into mechanical energy in which we drive our car. Okay, so now I've mentioned two kinds of energy to you, right? We've mentioned kinetic energy, right, which is how the molecule vibrates, translates, or rotate. And we're also talking about the chemical potential energy, and that's energy that's stored inside bonds, right? This chemical that's stored inside bonds, and sometimes when you break those bonds, you can harness that energy, as we've seen in biology, right? So those are carbon-carbon bonds. So generally, the more electronegatively similar to atom is, the more tension they have. You can think of two equals, right? When actually, that's not a good idea, because I was gonna say sharing means that they're better, but when they have same kinetic, same electronegativity, there's a lot of tension between that, for the electrons that's stuck between them. That's the short answer. All right, so the next up, system and surrounding. Okay, so we kind of talked about that. So the system's well-defined part of the universe that we are singling out. So that depends on scale of what we're talking about. Then surrounding will be everything else around it. Okay, in a closed system. Okay, we talked about that. So in closed system, no matter transfer, but energy transfer, yes. Open system, energy and matter can transfer. And isolated system, none of them can move in and out. All right, exothermic and endothermic. Have we heard of those terms? Yeah, exactly. So exo, ex, exiting, so out, endo, entering, in. Exothermic, releasing heat, out. Endothermic, taking heat in, right? So, in other words, if you see energy as part of the product, that's an exothermic process, because you have created some heat that can be released to the surrounding. If it takes heat into the reactant, so if you see a heat in a reactant or any kind of energy in a reactant, that will be an endothermic reaction. So let me ask you, photosynthesis and cellular respiration, which one is exothermic, which one's endothermic? So think about what I said about. Right. Yeah, exactly. Because photosynthesis, you're putting energy on the left side of the equation, right? You need sunlight energy. So that's an endothermic reaction. We're taking in energy. And then cellular respiration, right? We are releasing energy. Where? At the end, we're releasing it to that to those ATP synthase, right? We basically transferred it onto the synthase. Not the ATP synthase, onto the pumps, the proton pumps, right? So the energy basically, essentially, at the end, it all transferred through chemical potential energy, finally through the proton pump. Now we have that gradient, and it turns into mechanical energy as we turn that wheel that we call ATP synthase. Right, so heat. One measurement of heat that we always hear of is calorie. But surprisingly in physics class, they don't really make that much of a connection between calories and joules, right? At least not in our curriculum. I don't think that much. But right now, yeah. But right now, this number you should remember, 4.184, and that's one number that you need to remember in this chapter, joules, and that. Okay, there's two significance about that. Number one, it equals to 1 calorie, so that's a good conversion. And number two, later we're actually going to learn that this is the exact amount of energy that's required to raise 1 gram of water by 1 degree Celsius. Okay, so if you think of 1 gram of water, that's not a lot, right? 1 gram. Water is 1 gram per mil. I hope you know your density conversions well. So water being 1 gram per mil, 1 gram equals to 1 mil. So you can think 1 mil is very little water, right? A bottle of water is like 500 mil. So divide that by 500. So that very small amount of water, think about the amount of energy that takes to turn that, or not turn that, increase that temperature by 1 degree Celsius, 4.184 joules. That's why we say we use a different conversion. We just say, okay, that's 1 calorie. So that's a definition of 1 calorie. Okay. So heat is transferred from surrounding to system. So that'll be endothermic, as I said. Heat transferring from system to surrounding, that'll be exothermic. Okay. And that's just a visualization between system and a surrounding. Okay, so the next thing is a calorimeter. So there's a lab component to this chapter, and it always deals with a calorimeter. Okay, so if you were in school, you would definitely do this lab. Every single school has done this lab. I've never seen a school skip out on this lab. So we're building a container basically. So imagine in our school, we're probably going to use 2 styrofoam containers for this. So imagine you have 2 styrofoam containers in place of the green thing. So the green will be your calorimeter. You have some kind of heat source at the bottom. Okay, so I'll tell you what a calorimeter is first of all. So calorimeter is acting as a closed system. And actually it tries to imitate a isolated system too as well. Recall the difference. Isolated system does not let matter in and out and also energy. Okay. Okay, so those we call bomb calorimeters, the really good ones. But in real life, it's really hard. It's really hard to build something that you don't let energy in or out of it. Think about what's the what a thermos is doing, right? The thermos is one of those, those insulated cups that people bring to work and stuff, right? It keeps your coffee hot for like half a day or something. So that would be an approximation of an isolated system, right? It's trying to act like an isolated system where, of course, you don't want matter to go in and out. You don't want your hot coffee to go in and out of it. That's what any container is doing anyways. That's kind of what my water bottle is doing. But what my water bottle is not doing is keeping heat in and out of it as well, right? But that's what an isolated system will do. It will keep energy from flowing in and out of it. Okay, so that's what a calorimeter is the calorimeter is using that the isolated system to study certain reactions. So let's see, I'm not sure if they're going to provide us a calorimeter definition on Google is an apparatus that measures the amount of heat involved in a chemical reaction. Okay, because for example, here's what we're using it for. Think about this. If we want to measure, let's say a certain reaction. Let's say there's a reaction I want to measure, and this is exactly what we're doing actually. So let's say the reaction is the neutralization reaction between HCl and NaOH. Okay, so we have a strong acid here, we have a strong base, and you're familiar with that with the last chapter. So we got both of those things. When we know they're going to neutralize into sodium chloride and of course water. Now, but what if I need to know whether this is going to be an exothermic or endothermic reaction, right? Let's just say qualitatively. And later we can actually use this method to quantitatively measure too. And I'll show you how in a second. So you can either have heat on this side. So if you have energy on the right side, that means we have released energy, right? If we release energy, so let's say we have this calorimeter, we have this, some kind of styrofoam, and surprisingly, styrofoam cup works better than you would imagine, okay, and keeping energy in and out. But basically, we're gonna double cup it. So pretend we have 2 cups, double cup that. We throw in our reaction, so we're gonna throw our HCl into there. We're gonna throw our NaOH into there, and of course, we're gonna quickly close up the container. Okay, so then if we can assume that this is an isolated system now, of course we're going to have water as well. If we were to stuck a thermostat into it, okay, this is not a very good thermostat, maybe something like this. Okay, not a very good artist, but it's okay. I'll add some of this. What we can see is what we can measure the temperature change to infer whether energy has released or has been absorbed, right, by this reaction. Because if we're measuring this water, so now we can uh, make a call on what the system and surrounding is. So in this case, my system is going to be that reaction that I've described above, and the surrounding is actually the water. So you can think they're basically beside each other, they're touching each other because the water is all around that system, right? Because the system is basically the little ions that are dissolved in the water. So in this case, we're measuring the surrounding as the water. Does that make sense? First of all, because that sometimes that's kind of hard to imagine, because you're like, wait, that's the same thing. I thought the water that's reacting. Wait, no, no, no. The water is not reacting. It's the ions. Specifically, if you write a net ionic equation, it's really just X plus coming together with the OH minuses, right, into H2O. That's all that reaction really is, if you write a net ionic equation. Okay, so this is not writing very well. Okay, but the surrounding in this case is going to be water. Okay, so the system is the reaction, your surrounding is going to be the water. So as I said, so let's say I don't know what's going on right now. I don't know if this reaction is something that releases energy or it absorbs energy, but now I can tell. If I see my thermostat, if I see the, sorry, I keep saying the thermostat, the thermometer, if I keep seeing the thermometer increase in temperature, well, that probably means I have an exothermic reaction, right? Because I have released energy so that my system in the water has gained that energy and then thus increasing in temperature. Thus, you can think it's vibrating faster now. The molecules are going faster. Faster kinetic energy, higher at temperature. If on the other hand you see the thermometer starts to go down, that means your temperature is going down. What's going on? That means it got energy sucked out of it, right? That means that the system, the reaction, has sucked in energy. That means energy is on the left side. Okay, I'll tell you right now, this this reaction is actually an exothermic one. So neutralization reaction is usually going to be a exothermic reaction. Okay, so you can think of that's actually what the heat pack is doing too. So another way of thinking about this, heat pack, well, that's going to be a closed system, closed and not isolated, because the whole point of a heat pack is you want energy to be able to transfer out, or in the case of an ice pack, you want the energy to be able to transfer in. So then you can be the system basically. So when I maybe roll my ankle or something, right, I go take out an ice pack. An ice pack, and I'm talking about the ones that's not even in the fridge, right? There's some ice packs you can basically break it. I don't know if you've seen those. You break it. Basically, what happens is, have you seen those before? Yeah. Okay, so ice pack. So I think I've used one in middle school once. So it's basically some kind of these package. So what's going on in here is you don't need to keep this in the fridge. I don't know if they do this or not, but something like this. Hyper cool. So what's going on in here is there's two compartments you can think of, that's preventing the two things that are supposed to react together apart. So once you break it, then they starts mixing. Then what do you think? First of all, would that reaction be endothermic or exothermic? If it needs to turn cold, so then it can make you, exactly. It'll be endothermic reaction because it needs to suck in heat. Well, what happens when it's sucking heat? Then the surrounding gets cold, right? Then it gets cold, then it feels cold. Why does it feel cold? Because it's absorbing energy from you. On the other hand, a heat pack, something that you bring out maybe in the winter to warm up your hands, heat packs, you break that and there's some kind of reaction that does an exothermic reaction. Okay, in that case, see a toe warmer, hand warmer. So that reaction will be an exothermic, releasing heat. Thus, when you touch it, it can be transferred onto you. Okay, so that's enough talk about exothermic, endothermic, and all that. Okay, so calorimeter is basically taking advantage of that. Actually, let me take it one step further. And that's probably one of the calculations you will need to do later. So we can actually, I can give you an equation now, because this is a very simple equation, okay? Heat transfer, Q is heat, by the way, heat, and remember heat is always has to do with a transfer, so I'll just write heat of the system is going to be equals to negative heat of the surrounding. That's all it is. Heat of the system equals to negative heat of the surrounding. Okay? So think about what this is saying. If my system releases 500 joules of heat, right, negative, then the surrounding will be negative of that, which means it's positive, which means it's absorbing 500 joules of heat. As simple as that. So if my surrounding is releasing heat, if the surrounding is negative, then the system will be positive. So system and surrounding, whatever the heat transfer is always opposite sign of each other, indicating that one is absorbing, one is releasing. And of course, we can assume in a lot of these calculation cases that no heat is lost, which is actually a pretty hard approximation, because there's always usually some amount of energy lost. Yeah. Usually for our calculations. Well, a lot of the calculation we know are pretty theoretical. Okay, so another equation I need you to know now. Okay, this one it'll be a little bit harder to sink in, but I think this will be pretty interesting. The heat transfer of an object is going to be equals to mc delta T. Let's look at the individual components. So Q is the heat that I talked about, measured in joules. Okay. M is going to be mass of the object, measured in grams. And then temperature, delta T is change in temperature. So technically, delta T, delta anything is really just T final minus T initial, or T2 minus T1 temperatures. Temperature measured in Kelvin. Okay. It can really be Kelvin or degrees Celsius, because if you think about it, we're just looking at the changes between them, right? So, and they're in the same scale, because 1 degree change is the same, 1 degree Kelvin change is same thing as 1 degree Celsius change, right? The change is the same, but of course the absolute number is different, right? Because if we want Kelvin, we add 273. Okay, so that brings us to the C, because the C is really the one that we're not really sure of, but C is really a constant. So C is what we call, okay, so we'll give it a name if I can write properly. This is called a specific heat capacity. Specific heat capacity. If we look at its units, we can probably understand better on what it actually means. So before I give it the definition, I'll actually derive the units. So let's see. We have joules equals to gram times C. So C is the actual thing I'm trying to isolate here. And then delta T. Let's say if we're talking about Kelvin, let's do degree Celsius, since we're more familiar with degree Celsius. Degree Celsius minus degree Celsius, we still have degree Celsius. So therefore, if I were to isolate for the C, it's just going to be joules per gram times Celsius. So I just basically isolated that, right? So whenever you're not sure of the unit, you can always isolate if you know all the other units. Or if you want to know if you're using an equation right, you can always check the units, right? All right. So specific heat capacity. So look at this unit. Joules per gram degree Celsius. I think I actually mentioned this number a little earlier when I mentioned that 4.182, that value, because that is the value for specific heat capacity of water. This is how much energy in joules, how much energy does it take per does it take to raise 1 gram of water for 1 degree Celsius. Okay, so this is basically a constant that's going to be different for every single object. All right, so let's look at a list of some popular heat capacities. So specific heat capacity, and this is an appreciation of how special water is as well, because water actually have a pretty special value compared to a lot of other ones. So maybe this is a decent one. Let's just look. All right, so if we look at this chart, specific heat capacity. Oh no, this is not. This is like sapphires. Like these are like rocks and stuff. Okay, I need something more like common objects. Ah, there it is. That's more common objects. Okay, so here it is. So this is specific heat capacity for a lot of. So let's look at units first, because there's different units sometimes. So this is joules per gram Kelvin, which is same as ours, because joules per gram degree Celsius is pretty much same as joules per gram degree Celsius. Oh, sorry, joules per gram Kelvin. So if we look at water, so water is kind of like the standard we measure everything against. So water at 25 degrees Celsius is going to take 4.181 joules for every gram to raise 1 degree Celsius. Okay, so 1 joules per gram to raise 1 degree Celsius. If we look at some metals, so metals, let's find some metals here. Lead, iron. Look how small that is, 0 point something. Think about that. That's one of the first lessons that I remember learning from science class back in elementary school, actually in Hong Kong. It was a grade 2 science class. I remember they talked about the heat conductivity of metal versus like non-metal versus something like a rubber. They're like, oh, this metal spoon, you can feel it. You can it transfer heat very well. Well, why does it transfer heat very well? That's because it has a very low specific heat capacity, meaning it takes less energy to raise 1 gram of that substance by 1 degree Celsius, right? That's something that's easy to conduct heat. Whereas something like an insulator, maybe like a rubber, right? Rubber generally, that's why when you have a spatula when you're cooking, I don't know if you're cooking more nowadays, but the handle part is usually in rubber, right? Or some kind of material that don't conduct heat very well, so it doesn't burn your hand, right? So it doesn't burn your hand. And that part usually would have a high specific heat capacity because it takes more energy and more heat to raise 1 gram of that substance by 1 degree. Okay, so we understand this. So this allows us, so imagine if we want to know, for example, let's say a question is, so let's say what we can calculate from this. So let's say we have the amount of heat that's given. Oh, actually, I'll teach this from a perspective of the calorimeter. So pretend right now, going with the same story before, I throw in that acid and base for neutralization reaction into here. I have basically a calorimeter set up here. We call calorimeter is just a fancy name for this apparatus, this imitation of an isolated system, so I can study how much energy is released or absorbed in this reaction. Okay, so what are some data I can collect? For example, I can measure the initial temperature of this water before this reaction was started, and then I can measure the final temperature that this reaction was taking place. What quantity would that give me in this equation? Well, that will give me delta T, right? Let's say it went from 25 degrees to 30 degrees, then the change in temperature is going to be 5 degrees. Okay, so delta T is going to be 5 degrees. Think about what else I would have. I have the mass of the water, right? Let's say I have 100 milliliter of water. I basically have 100 grams of water. So actually, we can actually throw that in there to calculate. We have 100 gram of water. right? We know this value from the chart, and we can always consult our textbooks for these values if you don't remember. But you should actually remember this number, 4.181, 4.181, because that is the specific heat capacity of water, and again, that's in joules. So how much energy in joules it takes to raise 1 gram of that substance by 1 degree. All right. So 100 gram of water, okay, 100 mil. That's not hard to imagine. We have 4.181 as specific heat capacity. We also measured that the change in temperature is positive 5 degrees, because it went from 25 degrees. Okay, maybe I should write the whole thing down. So 30 degrees minus 25 degrees. Okay, that's not showing up very nicely, but okay, one last time. 30 degrees minus 25 degrees. All right, so actually I'm gonna make a quick calculation. So 100 times 4.181 and then times 5. Okay, so if we look at the units, gram is going to cancel with gram. Degree Celsius is going to cancel with degree Celsius. So those 2 degrees Celsius is going to become a single degree Celsius. You can cancel with the degree Celsius. So now I have joules. Okay, so I got 2090. Okay, 0.5, but I guess we'll include that part. But significant digits wise, probably is going to be important in this chapter as well. All right, so what is it saying? This is saying that water probably had to absorb this amount of energy, specifically 2090.5 joules of heat, right? Then what can we say about the reaction? We can basically say then this reaction released this amount of heat because of the positive nature of this. So imagine if the temperature was negative, right? If it went from 25 degrees to 20 degrees instead, then 20 minus 25, that would be negative. If the delta T is negative, then the whole value is going to be negative. Then you're talking about what? You're talking about the system, because we're talking perspective of the system right now, the surrounding water has released heat. So if in that case, then we can infer that the equation, so our reaction, probably absorbed heat. But let's stick to our present situation. In our present situation, our surrounding has a positive heat value, meaning it absorbed heat, endothermic. Well, if surroundings doing endothermic, then the system must have been doing exothermic, releasing heat. Does that make sense? And specifically 2090.5 joules. Okay? So you should let that sink in for now, but I'm going to take this one step even further. If that confuses you, I'm going to come back to this and talk about this part again. But now with this joules, I can actually calculate an enthalpy value. And enthalpy means this. Delta H is going to be equals to whatever Q of the surrounding. So this is the system, delta H. So I don't know if you've seen delta H, but you learned delta S before. Entropy. So this is enthalpy. So this is the system. Delta H of the system is going to be negative the surrounding heat. We know that actually, but dividing it by the number of moles. Okay, so number of moles. So this is number of moles. And then if I divide it on the other side, so this is basically saying this. I don't want to know the absolute energy released by my system, by my reaction, because that's going to depend how much of the substance I put in, right? Because think about this. If my situation right now, it depends on this 2000 joules, depends on how much acid and base I've included. The more acid and base I've included, the more energy it's going to release, right? Because think about it, if I put 10 mils of acid, 10 mils of base, it's going to release a certain amount of energy. But if I put like 500 liters, a big bucket versus 500 liters, that's not hard to imagine. That's probably going to release much more energy, right? So we want a standard value. We want a standard value that is per moles of a substance. And that's where delta H comes in. So that's why if we look at this, if I basically have modified this such that if I take this value now, the 2000 joules, and I go and divide it by the number of moles. Because for example, maybe I put 1 mole, then this will be 2000 joules for every 1 mole of acid I put in. If let's say I put in 2 moles for this, then I can calculate by dividing 2 that, oh, actually every mole actually only produces 1000 moles, 1000 joules of energy. But because right now I have 2 moles, that is 2000. Or maybe I put in 5 moles, then you divide it by 5, then it'll be about 400. So you get the point, right? Okay, so I'm definitely going to come back and revisit that. But right now, just know everything up to that energy transfer. Okay, Q in equals to Q out, or Q surrounding equals to negative of the Q system. Yeah, you can move the negative on either side. All right, I think this is a good time to take a break to let all that sink in. And I'll see you back in about 7 to 8 minutes. Okay? All right, see you in a bit. Hold up. No, I love this. I'm okay. Oh, yeah, yeah, please. Fuck. All right, hey Knock. Let's continue. All right, so we talked about calorimeter. We talked about how to define a system and surrounding. We talked about what endothermic and exothermic is, and we basically know that if we have a system and a surrounding well defined, then one is always doing an endothermic, you can imagine, and one is always an exothermic, because one is always going to be releasing energy and one is always going to be absorbing energy, right? Right, so let's see. Next slide. All right, so heat and temperature change. So how does heat transfer related to the change in temperature? That is the equation we just looked at. Q equals to mc delta T. So they wrote it as Cm delta T, but multiplying things, I think just rolls off the tongue better when I say mc delta T, because like mc square, mc. The specific heat is C of a substance is the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. So I think I've said that definition multiple times now. So actually, let's try a example question, and we'll do that one together. So let me just copy this one here, so we can do that. If I can find my mouse. My mouse just disappeared. That's so weird. Sorry, my mouse kind of just disappeared. Okay, got it back. So I want to put my question. Okay, here it is. Okay, so I think you can solve this. Try your best. So we have the equation basically right now as Q equals to mc delta T. Okay, the thing that's changing the temperature, you have to make sure the mass that you are using, so that M and delta T, you have to make sure they're on the same object. Okay, so in that last example, if I'm measuring the change in temperature of the water, which is the surrounding, you can't be using the mass of the system, which was basically the acid and the base, the HCl and the NaOH. No, we're not talking about that. We're talking about the mass of the water. Okay, so think about that. Right now it says if 150 grams of iron at 95 degrees Celsius is placed in an insulated container containing 500 grams of water at 25 degrees Celsius, and both are allowed to come to the same temperature, what will the temperature be? Okay, let's think about that for a second. Let's just guess roughly what's the temperature range that it could be at. So we say we have 150 grams of iron, so whatever that is, probably a piece of metal. Just think of a piece of metal. 95 degrees, quite hot. We're throwing it in a container, okay, insulated container. We can assume it's isolated system. 500 grams of water. We can consider 500 ml. Actually, that's a perfect bottle of water. Okay, so we throw that piece of metal in at 25 degrees. What do you think the temperature is? If you were to guess, give me an actual number, roughly. Okay, so here's why you pick 50 something, and here's why your answer can actually be improved a little bit. Your approximation can be improved. You basically pick the middle number between 25 and 95 because you're saying, okay, that's very good that you know that it's going to be somewhere in the middle between them, right? Because the metal is not going to get hotter, in a water that's lower temperature than it. The water's not going to get any colder by having some hot object thrown in it. That's pretty obvious. But the first thing you should notice is that there's more mass of water than metal. So do you think it's going to be closer to the water or closer to the metal in terms of the temperature it's going to end up being? Yeah, think in another way. Yes, that's the next thing I'm going to talk about. But first thing that I'm mentioning is the mass of this, right? So, yeah, mass wise, think about if I put like a hot marble inside like a spoonful of water. Think about how that affects the temperature of water versus if I put a hot marble inside the ocean. Which temperature? Yeah. Which temperature do you think it's gonna affect more? The temperature of the spoonful of water or ocean? Yeah, exactly. Because the ocean isn't going to feel the effect of it because there's so much more masses of water in there versus the mass of the marble. Whereas in this case, perhaps you actually have more marble than a spoonful of water, or or that ratio is much closer in this. So what I'm saying is, here looking at just the mass, I would predict it's closer to 25 than 25, 95. Okay, so probably in the 30 range, 40 range. But if you also look at the specific heat capacity, then it's really going to lean towards water. Because think about this, water has a specific heat capacity 4.181. Okay, iron has 0.41. Now, I'm going to give you my definition. This is how I view specific heat capacity. It's how unwilling is that substance to change temperature, to resist temperature change. So in this case, the higher number, the more it wants to resist change, the more it does not. You can almost think about it as like a heat inertia kind of thing, but not really. Okay, so water really doesn't like changing its temperature. Iron don't mind as much. 0.4 versus 4.4, right? That's almost a 10 times difference there. That's like actually exactly 10 times difference almost. So that means that iron is more willing to change temperature than water. So in that sense, it's also going to be closer to water's temperature then. Because water's resisting its temperature, right? Whereas iron is like, okay, you know what? You give me this amount of energy or I lose this much energy, I will have a more significant temperature change. So in that sense, I would actually now shift my answer to in the 20 range. I'm guessing it'll probably be more like 28, 29, at most 30. It's just from a guess, but we can actually calculate that. Okay, so we have basically two objects. We have the iron, we have the water. Okay, doesn't really matter which one you make the system, which one you make the surrounding, but one is probably a little more appropriate than the other here. Which one do you think want to be the system or surrounding? Sure, if you want to consider system as the water, I was actually thinking the other way around, but it doesn't really matter, right? Because you just got to know the interchange. So if we consider water as the system, iron as the surrounding, right? One's going to lose heat to the other. It doesn't really matter which one we label as which. All right, so a couple of things. We have the mass of the iron as 150 grams. We have the mass of the water as 500 grams. Second thing is we have their initial temperatures. T1 is going to be 95 degrees Celsius here, and T1 is going to be, oh, my pen, okay, 25 degrees Celsius here. All right, and both are allowed to come to the same temperature. What will that temperature be? So we just don't know what the T2 is going to be. But we know that they're going to be the same value, right? So kind of related to math, but we can give that a letter. So perhaps we will give it as x. So let T2, we'll let that be called x. T2, we'll let that be called x. Okay, because we're expecting them to be the same number. Okay, so we actually don't even need to consult the chart. because they're giving us the specific heat capacity. So C equals 4.18 joules per gram degree Celsius. Now, just watch out for this units. Look at this. Whatever heat capacity it is, so this is right now in joules per gram per Celsius. I'll show you how they can change. For example, this joules could be actually in kilojoules. Well, if it's in kilojoules, then the energy that you end up calculating at the end will be in kilojoules. That's all it is. If you see it in kilogram at the bottom instead of grams, then just make sure that your mass that you put into calculation is in kilograms. If the degree Celsius, you find it in another unit, for example, Kelvin or even Fahrenheit, then you make sure the change in temperature that you put into the equation is exactly that. So all I'm saying is have to always pay attention to the units of C. Okay, but right now it's the one we're used to, joules, gram, Celsius. And that's all the stuff we have, so we're okay. Okay, oh, whoops, I switched this around. This should not be 4.18 because iron is the 0.444, whoops. And then the other one, C is going to be, so that's C is going to be 4.18 joules, 4.18 joules per gram degree Celsius. All right, now we can use our trusty equation. What was that first equation I gave you? First equation I gave you was Q of a surrounding. It doesn't really have to think in terms of surrounding or system, but I'm just saying that so you understand that there's nothing else in this universe, right? In that specific universe, you're either transferring from one or the other. So in this universe, there's only iron and water. So we're basically saying Q of the surrounding is equals to Q of the system, but one of them needs to be negative. Okay, that's just to say one is going to be negative of the other. Q of the surrounding. So maybe I'll just put on the surrounding for now. So negative. Okay, but specifically, what are each of these Q equals to? Each of these Q's are equals to MC delta T. So now I can actually say that negative, this whole thing, MC delta T for the left side is equals to MC delta T on the right side here. Alright, so now we can actually sub in everything because we actually only have one unknown variable in here. Okay, so hopefully you're doing this on your paper as well. So we got 150 grams of iron. Okay, we're timesing it by, or we're multiplying it by 0.444 grams, sorry, not grams, joules per gram degree Celsius, and then we're multiplying it with T2 minus T1, but T2 is an unknown, so we're just going to put it in bracket X minus 95 degrees. Okay, so since we already predicted, this is probably going to end up being a negative value if we ignore that negative at the very beginning of the bracket, because M is going to be positive no matter what. Mass has to be positive. C is going to be positive, right? Because to raise energy, we usually, I don't think we ever going to have a situation where we lose heat to increase temperature. So you're always going to have a positive energy value to increase by 1 degree Celsius. So delta T in this case, we predicted it's going to be, the final temperature is going to be between 25 to 95. So we can already see this is going to be a negative value. Okay, so we can see why. On the right side, well, on the right side, you're going to have the other way around. You're going to have a positive value, right? So that's why we put the negative here, then left side equals the right side. Negative surrounding equals the Q system. Okay, let's keep going forward. Now, on the right side, we're going to have 500 grams times 4.18 joules per gram degree Celsius, and then multiply that by 25, so X minus 25. So that's the final temperature, that is the unknown, minus my initial temperature for the water, because remember their initial temperature are different. One started at 95, one started at 25, and they meet in the middle. Okay. So actually we can make a calculation from this. So on the left side we have 150 times 0.444. Right, we could distribute it into the brackets. Right, so in that case we'll have 66.6, 66. Oh, my thing is not writing very well at all. Alright, so 66.6. That's going to be x minus that one times 95. 6327. And don't forget that big negative sign on the outside. And that equals to, on the right side we have 500 times 4.184, or 4.18 in this case, and that'll be 2090. My pen, 2090. Okay, so what is the x? 27. See, as I predicted, it's going to be much closer to the water than the iron, right? So, sorry, what did you say x was again? Which is T2? 27. Okay, 27. Any decimals? Okay, 0.12. Okay, this is really 27.12, and that'll be in degrees Celsius. Okay, so you should know how to do these kind of problems now. So these are the problems where I say you throw in two objects and you know, you find out the final temperature. Sometimes they give you final temperature and you have to look for a specific heat capacity. Okay, so if I were to graph that in terms of a progression versus temperature, then it will probably look something like this. So that's the one that started at 95. 95. And we're going to see the initial rate, and you learned calculus, so you should know this. The initial rate of change of this temperature is going to be quite drastic. Then it's going to hit an asymptote in that final temperature. It's going to be like this. And then whereas the other one, the water started at 25 and it didn't really change much. So probably like this. Probably looks like that in terms of the graph. Alright, so now we can go back to our slide. Alright. So energy and enthalpy. So now we can properly define enthalpy. If this response I think the slide is a bit . Okay, so well, it's because they have a little video thing. Okay, so in this case, they're saying in a calorimeter, the water is the surrounding. Okay, so your water is surrounding, and and in this case, negative delta H. Negative means an exothermic, so it's probably losing heat, and then the system is absorbing the heat. All right. So molar enthalpy is when you adjust it to 1 molar. So that was the thing I was talking about earlier. Well, sometimes knowing the absolute heat that's released or absorbed in a particular system is not that useful, because we want to be able to compare between several different reactions or compare different quantities. Then there's no sense in comparing. For example, if I want to know the crop production, right, between countries, there's no sense talking about the absolute crop production, because if you're looking at something like U.S. versus, like, let's say Hong Kong, you're going to see the amount of crop production is going to be very different between the U.S. U.S. is much bigger area, but if we adjust it to the area, or actually not crop production, let's say like a product, GDP. You've heard of GDP. So that's is adjusted per person, right? GDP is per person. That makes more sense, because you want to know how much, not as a whole country can be able to produce, but how much is production per person. So in this case, it's how much energy per 1 mole of certain substance. Okay, so it's adjusted, makes for better comparisons. All right. So there's different types of molar enthalpy. I don't know why these slides are not really showing. Okay, I guess there wasn't. Okay, so I think that one was just to show you that there's different types of molar enthalpy, as in there's different types of reaction. So there's enthalpy of neutralization reaction, that'll be for neutralization reaction. There's an enthalpy of solution, so that'll be for dissolving something. Enthalpy of combustion, so that'll be the enthalpy change associated with combustion. So that's just related to the different types of reactions that you can have. Okay, so enthalpy of reaction. So what do I want to say here? So H is an extensive property. So delta H depends on the amount of reactant and products. That's what they're saying. What is the delta H for the combustion of 11 grams of methane in excess oxygen? So now we can actually turn to our textbooks, because now we're going to consult a chart at the back. So you're going to see that there's actually a chart, and I was trying to pull up one from the internet as well. If you look at page 799, that gives you all of the standard molar entropies as well as the enthalpies of formation. So I want to describe to you what that chart is saying. Okay, so tell me once you're at that page. Yeah. Okay. So what this chart is telling you is, have you seen this chart for entropy before? You've done it for entropy, right? Because I feel like we've talked about entropy before. Okay. Okay, so something like this, first of all, if you don't have your textbook filled up. So on a chart like this, it basically gives you how much is the energy change. So notice the unit there for delta H is kilojoules per mole. Okay, so this is not the chart I wanted. Okay, so kilojoules per mole. Actually, as I have pulled it up on my screen as well. So those are the list of. Oh, so this one only has the enthalpy of formation. So this is saying at 298 Kelvin for temperature, because this depends on temperature, the enthalpy changes. Let's say something like ammonia NH3. At 298 degree Kelvin, it actually releases heat when you are putting together NH3 from its own element. So formation, heat of formation basically means NH3 coming together from its elemental forms. In this case, it'll be nitrogen and hydrogen. So those individual atoms come together and bond together into ammonia. 1 mole of that will release 46.19 kilojoules of energy. That's what it means. All right. So it doesn't always release. For example, if we look at acetylene is not on our textbook, so let's pick something else. Calcium carbonate. So if we look at calcium carbonate, sorry, that's another negative. I'm looking for a positive value. Benzene. Okay, benzene. If we look at benzene, to actually put that together, it actually requires 49 kilojoules of energy because it absorbs. You can see it positive. It's an endothermic reaction when we put together the C6H6. So what you can see is that the reaction basically is the formation, because this is heat of formation, so it's the formation of that compound from atoms of the natural state. So that's why we actually don't see any atoms in its natural state. For example, we don't see a delta H value for the formation of oxygen O2, for example. And that's because it's 0. So any atom, when you see it on its own, even if it's diatomic, actually diatomic is its natural state. So Hofbrinkel stuff, H2, Cl2, Br2, I2, all the Hofbrinkel, I think you might have learned it in a different acronym, but all your diatomic molecules. Those are already, as long as they're in gaseous form, because it also has to be in their standard state as well, at that temperature, at room temperature, 298 Kelvin. So if at room temperature, so for metals, it'll be solid generally, right? For those Hofbrinkel stuff, it'll be in gases. If you only see them in your own element, and it's in the state that's appropriate for that temperature, then the heat of formation is 0. Okay, because it doesn't take any energy to form it. Oxygen, O2 at room temperature, it's just in that state, oxygen, so it takes no energy in or out for it to be in that. All right. So here, delta H for a combustion of 11 grams of CH4 and XX oxygen is going to be a negative value here. So we can actually calculate that from our textbook. Okay, so here, imagine this was our problem. Imagine our problem just says this right here. And this is our next type of problems that we need to learn how to do. So this is getting away from that Q equals MC delta T stuff. So that stuff you can definitely review. And there's a lot more we can talk about that. But I know you're going to study. So this is just like a little preview session so you can get started on learning this stuff on your own, right? So if I want to know the delta H of combustion of 1 gram, I must tell you this equation. This is the Hess's law. So first of all, let's write in the reaction first, because combustion of CH4 we both know is going to be CH4 plus what? Yep, CH4 plus oxygen gas, and then yep, so giving you H2O and CO2. Exactly. Alright, so what I'm saying is the delta H of reaction can actually be calculated using this equation. The sum of all the products, so don't even worry about that sign for now. if we take the number of moles, so the coefficient in front of our balanced equation, in this case, are we balanced in this case? We are not balanced, so we need to just put a 2 here, and then we just need to put a 2 here, right, on the oxygen. Okay, so whatever you take the coefficient, you multiply by their delta H of formation, okay, of the, and then we're basically gonna take the product. So we take each of the products. So in this case, the H2O. We're gonna take H2O. We're gonna check the chart at the back, the delta H value, right? It gives us kilojoules per mole. And then we multiply by mole value by the coefficient. So in that case, it'll be 2. Okay, this is really difficult to write in. Okay, sorry, you got this. And we basically subtract it with a the reactant version. So we add up all the product. Okay, this is really hard to teach like that. I'm going to copy this whole thing. It's really hard when this thing is lagging a lot. Okay, so delta H of the product minus all the delta H of the reactants, and as I said, you need to actually multiply by the coefficient. And I'll actually write out the full formula in 1 second. So that's basically saying I'm going to take all the products. In this case H2O and CO2. I'm going to multiply their moles. So H2O would have 2 because of the coefficient, 2 moles. I'm going to times by the delta H value that I can see at the back of the textbook. So what is that? What is the delta H value for water? So I think we're still back at, what was it, 799? Yeah, page 799. Yep, can you tell me what that value is? Liquid. Well, actually H2O can't really be aqueous. H2O. Oh, that's on the back page, isn't it? Yeah. H2O, yeah, so negative 285.8, right? Yep, so 2 times that, and then plus what? We're summing all the products, so another one would be CO2. And what's the N for CO2? So it'll be 2 moles. Whoa. Can you try writing this? Actually, no, you don't have a pen, right? 2 moles times negative 285. You know what? I have a plan. Give me 1 second. Okay, so hopefully that's gonna improve things a bit. Oh yeah. So wait, it was negative 285.8. Yeah, did you find one for carbon dioxide? Okay, negative 393.5. Okay, this is, I'm just gonna have to do this.